Um,
Okay. Hey,
Great.
Anton, welcome. Let me pin myself as
So
well.
thank you for having me, guys, today.
Yeah, so
So I've prepared a presentation to talk about all the bits and bytes and consensus algorithms of Spacemesh, which I can run through, or we can have like a question answer session, or both, like whatever you guys feel is best.
I think probably makes sense if you want to get started, give the introduction, and then we can leave the latter part for questions.
Cool, great. So just share the screen. Not this one. Okay. Second. Great. Thank you guys for joining me today. My name is Anton, and I'm gonna talk about Spacemesh, which is basically a new block mesh protocol we're building. And it's based on proof of space-time, which I'll elaborate about later. And as I said, my name is Anton. I'm a developer at Spacemesh. I've been there since almost the start for almost 3.5 years now. I've been their second developer. So I've actually come to see this whole big thing come to life, which is super cool. If you have any questions after this talk or want to contact me later, you can do that through my LinkedIn profile. So, and I'll let you have the presentation if you have, like, if you want it for later. So, what are we gonna talk about today, basically? So we're gonna, this is the blockchain club. I assume you all know what blockchain is, but we're gonna run through it really, really quick, just to see how Spacemesh differs from other older blockchains, and what does it really aim to solve and how it solves it. So we're gonna basically talk about blockchains and the global ledger, and we're gonna talk a little bit about the Nakamoto consensus, its advantages, and then we're gonna talk a little bit about proof of work and its disadvantages, and how Spacemesh was built to overcome these disadvantages and create something that is, we feel, is truly sustainable blockchain, block mesh, actually, that will that basically takes like the lessons from past blockchains and tries to solve them to create a more sustainable blockchain that can be run for decades and ages eventually. So, and then we're gonna walk through some of the protocols of Spacemesh. And feel free to ask me anything about the protocols when we discuss them, and anything at all during the presentation. You are more than welcome to ask me questions. So let's start with the basics, with the real basics. So a blockchain is basically a network of computers. They're usually connected through a peer-to-peer network. They're distributed, meaning that there's usually, in most blockchains, there's no centralized authority or centralized location where the blockchain runs from. Usually what the peers in this blockchain contain is what we call a append-only ledger, sort of a shared database that all nodes have the same exact copy of that database. And this is what the basically what the blockchain sustains. What it holds is this huge database, and this is where we keep our information. Most, not all, but most blockchains are decentralized, meaning that there is no central authority or location that basically controls all the nodes. And again, most blockchains are permissionless in the sense that anyone is supposed to be able to join, participate in the consensus, have its own copy of this append-only ledger, and also mine coins or receive rewards for sustaining this blockchain. Okay, so we all know that. This is why it's called a blockchain. It's basically a list of blocks. This is how most blockchains operate. And blocks usually contain transactions. Sometimes, if there is what we call a global computer, it will contain smart contract code that can be run on each node and will form some modifications to this global state. And sometimes other metadata, such as general data you want to put on the blockchain and have it kept there for basically forever until some algorithm comes in and clears it away. Mining is basically the process of creating blocks, and most blockchains define that if a miner does create a block and its block is considered as valid, it will receive a reward in form of currency coins to its account. So this is how I'm not going to say old school, but most blockchains till now work. You have, okay, so let's define a global ledger. Basically, a ledger is a database that contains all the valid transactions ever made, should be. It's replicated among all miners, as we said, meaning that the same state should be exactly the same in every miner. This is why we call it a replicated state machine. In Bitcoin, we agree on this state following what we call longest chain rule or Nakamoto consensus. Okay, so what does it mean? Nakamoto consensus basically means that for a miner to know which transactions are the valid ones or which transactions should be inserted into that global state we've talked about, it basically looks at all the blocks it knows and have received from other nodes and simply looks for the longest chain. I mean, the longest chain of blocks that point one to another. And once it thinks it knows what is the longest chain, it will usually take these transactions and apply it to the state, meaning perform the transactions and alter the global state, as we said. So usually we need to wait 6 blocks to point at one another. And if we have 6 blocks pointing at a certain block, then we call it valid. Then we know it's with very high probability. The transactions in this block are valid, and we can definitely apply them to the state without having to fear that these transactions will be reverted by another longer chain that will overtake this chain. And this is due to the fact that, as I'm going to talk about later, it's very hard to create these blocks, and it requires a lot of work to create these blocks. And if someone, and it's very not likely that a malicious entity in the network will be able to create this much work to create 6 other blocks that will eventually alter the state of the blockchain. Okay, so I assume most of you know that. If there are any questions, so let's go on. So we have blockchains, and as we said, they are decentralized and permissionless, meaning that everybody can join and participate in the consensus of these blockchains. And this opens up a lot of opportunities for malicious miners, malicious entities to try to attack these networks and these chains in order for them to gain, obviously, currency, control over the network. Sorry?
No longer based on punitive throughput metrics, but rather based on the physiology of the human people. We achieved upwards of 60% reduction in.
Great. Okay. Sorry. So anyways, what kind of attacks can we expect to see in these kind of blockchains? So the most prolific attack, the most dangerous attack is the double spend attack. As we said, each block contains transactions, and a transaction is basically this address wants to give this address this much currency. And if a malicious entity somehow can create a situation where some coins that have been spent and sent to one account can be resent and still considered valid to another account, this is basically double spend. And if you do it long enough and many times, you basically print money this way. So this is a very devastating attack, which most blockchains try to avoid and have very a lot of security measures to prevent it. Another attack is eclipse attack, where some nodes may not receive all the information as other nodes in the network, thus thinking that the global state is different than the global state in the rest of the network. And this can cause also maybe double spend attack, but maybe simply misinforming other entities that use that node as gateway, making some clients of that node think that the state is different than the actual state. There's also a 50+1% attack. Since consensus is made by the majority of the network, usually, if you have more than 50% of the network, you can basically decide what is the correct chain, simply by extending the chain that you want and not the chain that follows the rules of Nakamoto consensus, meaning longest chain rule. So this is another way to skew the global state to the desired state that the attacker wants and not the real state. And finally, we have SYBIL attack. And basically a SYBIL attack is a small number of entities that can counterfeit multiple peer identities so that they can falsely make the network believe that they have a disproportionate share of the system. So this is how a 50+1% attack can be made if we didn't have countermeasures in current blockchains. So again, all these attacks are for a malicious entity. All these attacks allow a malicious entity to change the consensus, change the global state, reorder or censor transactions so that it basically controls which transactions are allowed to be inserted into the state and which are not, and basically make other nodes have the wrong image of the current state. And Bitcoin, okay, so it's a very devastating attack, and we would like to solve it somehow. And there are currently different ways to solve it. So in Bitcoin, another proof of work consensus, it's called proof of work. Ethereum will use proof of stake. meaning that some currency is staked for the eligibility to validate transactions and insert them in blocks and eventually into the blockchain. And we at Spacemesh use proof of space-time, about which I'll explain soon. So let's talk a little bit about proof of work. Basically, proof of work means that in order for you to create a valid block, you need to include in that block some sort of a random number that solves a cryptographic puzzle, or even in other terms, matches certain criteria that the network has defined. So if a number is found, the miner is basically eligible to mine a block. It will put this number into the block and release it to the network. Basically, once this block has been released, it's still not guaranteed that this block will be included in the network, because there is no guarantee that at a certain point in time, only one miner will be able to create this block, thus creating some sort of race between miners for who gets to publish its block faster than all others, and propagate it to enough nodes in the network so that they will all agree that this is the correct block and not another block. So basically, this is what causes many miners to spend a lot of energy and resources running multiple GPUs and custom ASICs to find that random number, to find that cryptographic solution to the puzzle as fast as possible. And it's creating some sort of an arms race between miners to get the most GPUs and the most hash power between themselves, and also run in areas where electricity is cheaper and cooling is cheaper. And this basically creates a situation where only some miners that have all these custom ASICs and have the most hash power to mine these blocks are basically the only ones that can participate in this blockchain. And it hurts the, okay, let's talk about this. And it basically hurts the amazing property of decentralization of the network. So as I said already, we have certain issues with blockchains and proof of work. Basically, there is very high competition over creating blocks, because miners are trying, all the miners are trying at once to create these blocks. They're basically in a constant race to do it as fast as possible. This causes very high energy consumption rate for mining. And at a point in time, 2% of world's energy consumption is wasted on mining. And I say it's wasted because most of the energy that is spent on creating these blocks often don't get rewarded in coins, because you may invest time and energy to find that random number, but until you find it, you sometimes are overtaken by a faster miner. And this means that all of your work has gone to waste, okay? And obviously, it means that miners, for them to mine, need specialized hardware. And this in turn means that not everybody can mine. I mean, nobody here can mine Bitcoin on their personal computer. And it's causing a problem because it makes the protocol very centralized. Like at a certain point in time, before China had all these regulations about mining, more than 50% of the miners were located in China. And this means that basically, if all these miners will decide to collude, and then they can overtake the network. Basically, they would have more than 50% of the hash power of the network, and they could have decided and census transactions according to their will if they would collude. And basically, there is no way around it, because for someone to compete with these miners, they will have to invest a lot of time in custom hardware and find a place where mining is cheap enough in terms of energy and cooling, which is kind of hard to find all over the world, and only in certain places it becomes profitable. So all these issues are basically issues of Bitcoin, which was the first real decentralized electronic cash system. And Bitcoin is great. Bitcoin is super easy to understand. It's super easy to implement. Nakamoto consensus is very easy to understand, and it just works like magic. But now, 13 years after Bitcoin was launched, we see its drawbacks. I mean, now we see that it's not really sustainable to keep mining Bitcoin, and it's not really decentralized as the original intent was. So we're in a bit of a pickle here, and this is where Spacemesh comes in, basically. So Spacemesh is a block mesh technology, and it utilizes proof of space-time as a scarce resource to participate in the consensus protocol. Basically, we aim to be a more environmentally sustainable protocol because we have much less energy consumption. We are a race-free protocol, meaning that every miner that have spent some work and have staked space on its computer will receive a reward, basically, and miners are not competing one another. Instead, they're working together to extend this global ledger and to validate blocks together, and they also share rewards. There's very low barrier to entry and to start mining Spacemesh because everybody has storage on their computer, and since there are no additional requirements except like free storage, so everybody can join. And this means that our network will have a really long tail. I mean, we're not effectively, we welcome whales as well. I mean, people who will build custom mining rigs with a lot of storage, but we will still have this long tail of home miners, hopefully, that will keep sustaining the network and keep it decentralized as much as possible. So let's talk a little bit about how Spacemesh actually works and what gives us all these great properties we've talked about. So as I said before, Spacemesh is a block mesh. By the way, does someone have any questions about the blockchain part and Bitcoin part of this talk? Yeah, great. So I'll continue. So basically, in a block mesh, at a certain predefined time slot, there is no one block that's created, rather than multiple blocks that we call a layer. So imagine a Spacemesh protocol is divided into time slots that are called layers. And in each layer, somewhere between, and it's a predefined number, 50 to 200, and that depends on the configuration of the protocol, obviously, are created at once. So each block is created by a different miner. this means that all the miners that wish to participate will eventually get the chance to create a block and receive a reward for it. Another great attribute is that the reward is shared among all miners that produce the block. So there is no incentive really for miners to hold on to transactions and do what is called selfish mining, or not produce a block when they should, because they can't gain any advantage, because each miner basically knows at which layer it needs to produce this block. And for this block, it will receive the reward. So layers are divided into larger time slots, called epochs. And the difference between each epoch is how many miners are eligible to participate and create blocks in that epoch. I'll soon explain a little bit about it as well. So how does it work? Basically, we have, as I said, an epoch, which is a set of miners that will create blocks. And at a certain point in time, many blocks are created to form what we call a layer. How do we reach consensus, basically, using this topology? So it's a bit trickier than blockchain, but we'll try to walk you through it. So the first consensus algorithm is the tortoise algorithm. This is a slow, relatively slow algorithm that it's not interactive, meaning that the miners don't have to communicate between themselves to reach consensus on which blocks are valid and which are not. And the tortoise algorithm basically is a vote counting algorithm. So for each block, you count how many other blocks see it and mark it as valid. Once for each block, the number of positive votes for it passes a certain threshold, so you consider this block as valid. And this is how throughout the layers, a block will gain more and more positive votes. Eventually, after it passes the threshold, it will be considered as valid and put in the global state. Okay, so since this is not interactive protocol, if blocks or miners that create the block don't vote the same, it can take the other blocks that came before it a long time to pass the threshold. And this is why this algorithm is called the tortoise, because sometimes this vote counting algorithm may take a while. I'm also going to share like a bit. When we first wrote the tortoise, it was super slow, and because running all these matrix of blocks pointing at all the blocks in the past took a really long time before we optimized it. So this is why also the initial non-optimized solution for this vote counting took a long time to calculate. And that's why it's originally called the tortoise. So this is basically how it works. For a block X to know what its opinion on block E, it needs to see what all the other blocks starting from the layer after block E and until block X think about block E. Okay. I hope it's you understand it, but basically, so a block X now needs to ask each block, block F and et cetera, what does it think about block E, whether or not it's valid or not. So it then counts all the positive votes the other blocks have on block E. And if it passes the threshold as such a same as block D, it will be inserted into the global state. This algorithm is recursive because block F's opinion on block E is the sum of all blocks, all other blocks' opinion on block E. Okay, so this is why it's initially it was very hard to calculate this recursiveness all the time, and the non-optimized algorithm basically means that each block has an opinion on every block till genesis. Okay, so we obviously made some adjustments so that once it passes some threshold, we don't need to keep it in the memory, but this is the original, how the original algorithm works. So I've talked a little bit about how the mesh works, and obviously we can see a lot of advantages in having multiple miners validating blocks at the same time. So if we have a layer that supports many blocks, we basically invite more miners to participate actively because they'll receive rewards. And as I said, there's no race between these miners because every block produced is basically included in the mesh. It's a more secure network, as I said, because there is no single miner that decides about the validity of the block before it. Okay, not the case in proof of work and chain algorithms, where single or different miners decide on one block whether or not it's valid or not. And this also means that transactions are less likely to be censored because transactions are included by all the miners, not only by one miner. This means that basically there's no single point of failure in this algorithm. So as I said, if by any chance miners don't see the same network or mesh image, and they happen to vote differently about different blocks, it might take the tortoise algorithm a long time to reach these thresholds and validate blocks. So we thought about and implemented, obviously, another consensus algorithm that helps the miners of this epoch to reach consensus over the valid blocks of the previous layer. So this makes all the miners in a certain layer, all the honest miners, obviously, vote the same about all other layers. And this helps converge these positive votes a lot faster. So in fact, when using the HARE algorithm alongside the tortoise algorithm and causing all miners to basically vote the same because they participated in this consensus algorithm, so blocks are being validated within the time frame of one layer. Okay, so we have enough positive votes in one layer pointing at the previous layer to make all these blocks valid. And basically, this helps the network and the state to advance a lot faster. So unlike the tortoise algorithm, the HARE algorithm is an interactive one, and it's a leader-based consensus algorithm, and it's a bit trickier than the previous algorithm, basically because it's an algorithm that works in rounds, different time slots. And in each round, the participating miners exchange the relevant information for them to decide and agree on the correct set of blocks to vote for. Okay, so the first thing a miner that participates in this consensus algorithm will do is basically it will share all the current view of blocks that are valid. This is just to get to the state where basically all miners start with the same number of blocks they see or know as valid, usually. And then all the miners that participate in this protocol broadcast their updated view, meaning they broadcast what they see after everybody has exchanged the blocks. Then each node broadcasts a proposal to the group based on the status round. And this proposal is basically the proposal for which blocks would everybody vote, okay? So as I said earlier, this is a leader-based consensus protocol, but the leader is only selected after this protocol runs. And this is to avoid situations where a miner knows it's a leader and will mislead all other nodes with its proposal, okay? So after this round is done, each active participant determines who is the leader, and according to the proposal of the leader, it basically commits on which valid proposal it will vote for, meaning all other miners select their leader independently. Usually it will be the same one, and they take its proposal and submit it as their own, meaning this is the proposal I will vote for in my produced block. After all or most honest participants commit to this list of blocks, we have a notified round where each node or active participant basically releases all these commit rounds or commit messages that all the nodes have sent. And this is to basically signal the entire network that consensus has been reached and enough participants in this consensus protocol agree that this is the list of correct blocks to vote for. And since this round, when this round is done, basically all nodes, not only the participants in this consensus protocol, know which are the correct votes, the correct blocks, I'm sorry, to vote for when they produce the block. So this is called the HARE consensus because it's obviously converges votes faster. But in fact, this is the slower one because we have 5 rounds and each round takes a little bit over, it takes about 30 seconds of communication so that all the miners receive all these messages and we'll be able to go to the next round so that this consensus protocol may finish. So basically, this is how we converge and know which blocks we should vote for when a miner produces a block. So there's a little bit of another small consensus protocol, and this is like the fail-safe of the system. So what happens if there was an attack on the HARE protocol, and by chance, the elected miners to run this protocol are malicious and has somehow caused the protocol to lag and not to produce results, which is possible, okay? And not produce results within a certain amount of time. So this means that blocks won't pass this voting threshold so fast. So what happens? How will a miner decide what to vote on other blocks if it doesn't have the HARE results? So this is where self-healing comes into play. And self-healing is another protocol that basically it tells miners that if they don't have HARE results, they can vote, they need to vote on these blocks they didn't pass any threshold with this a decision made by a coin toss, okay? So imagine they all have this random magical number that each layer basically tells them whether the coin is on the plus or on the minus side, okay? Heads or tails, let's say. And basically, this is the fail-safe to make sure that enough miners vote the same. Because this coin is shared through a different consensus protocol to all the miners, basically all the miners still have some sense of how to converge their votes together, okay? And it basically doesn't, it's not that important if they vote for a block or against a block, as long as they vote unanimously, okay? So this is like the final algorithm that is aimed to run only when network is under severe attack and when miners are unable to reach a consensus in a standard way through running HARE protocol and then voting as the voting for the result they received in HARE protocol. Okay, any questions so far? Are you guys awake? Cool.
Hey, just real quick, I just wanted to just make sure that if you guys have any questions, just let us know while we have Anton on. I think he has a bit more to present here, but I think we only have around 10 more minutes. So just want to make sure that if you guys have any questions, you kind of do now.
Oh yeah. Yeah, if you guys have questions, I'd rather take questions than run you through the entire protocol. But if not, I mean, the rest of the stuff are quite interesting as well. So
okay, let's just keep going then.
Cool.
So, actually, can I ask a question? Would that be okay?
Yeah, sure.
Yeah, so I guess I wanted to ask just a little bit high level. Anytime you're designing a protocol, you need to make a whole bunch of design choices, right? And if you look at sort of other proof of space-time or maybe proof of archival protocols, something like Filecoin or maybe Subspace, they've made the choice to, rather than just fill the disk up with kind of random encrypted stuff, to actually put some sort of content in there. Yeah. And when you make that choice, you also make another set of trade-offs. Like in the case of Filecoin, it's highly targeted towards what I would call enterprise-grade data storage providers. How do you think about some of the trade-offs that you've made in this protocol versus the other ones? Is the reason to put random cryptographic stuff in because it's simpler to design and quicker to deploy that way? Or are there other trade-offs that maybe we should think about if we were headed down this path of designing something new?
So I think the first consideration is the network security. We feel that this method is a lot safer and is less prone to forgery. Okay, so it's a lot easier to forge files you've stored on your storage. Okay, and it's a lot easier to trick protocols such as Filecoin. Okay, and this is like the main concept that we want to have. Like, we want to be like a really secure Bitcoin style protocol. Okay, so we have decided to forego all like other utilities this chain or mesh may have for the sake of security. Okay, and so yeah, so this is the main main reason we chose to store these special data structures, as opposed to storing something that actually makes sense to store. But let me see if they're like, in comparison to Filecoin, if I can think of any other reasons. Basically, no, I don't think so. I don't think so. And also, we want to have as many miners as possible, so everybody can decide on the amount of storage it takes, and still be able to participate in the protocol. Okay, so we really want this protocol to be available to everybody. Okay, and especially home miners. Okay, so this is also the main reason we chose to design this protocol this way.
Cool. And then I guess a follow-on question. So, with security being the highest priority, the minute you add sort of an EVM style virtual machine to your protocol, then what happens is, if you have a Bitcoin style protocol, at some level, the order of the transactions, it's not that it doesn't matter, but it matters less. You could still have a double spend attack or something, but the minute you have an EVM there, then that problem becomes much more complicated. Is that the reason that you've chosen essentially not to put an EVM style virtual machine in?
So we have an EVM in the planning, and it is a difficult problem to solve, because you're correct. Like, it's a lot easier in a chain style state, because like current blockchains that have a global computer or a VM running, so they can simply stamp the current state and have it in the next block. So here it's a bit trickier, because still miners need to somehow agree, or at least know that they have the same state, and still be able to run transactions. So it's not an easy thing to do, and I can disclose that we're actually still working on that part of agreeing on the global state somehow, like in the same sense that Ethereum, for example, have the hash of the global state in each block. So we try to either have it in our blocks, or have some sort of guarantee that once we run Tortoise protocol, and Tortoise protocol validates the blocks, so we are very, very confident that these transactions are the correct ones and won't be reordered or reorg.
Okay, yeah, thank you very much.
Cool. Any other questions, by the way? Cool. Let's go on then with the proof of space time. So how does proof of space time basically works? You simply have to initialize or write a certain data structure on a certain amount of storage. You need to store it somehow. You need to store it on your storage for a certain amount of time. In Spacemesh, it's basically an epoch's time. And after this epoch is over, you still need to prove that this storage exists. And if you prove and you publish the proof that you have still stored this storage, you basically are now eligible to mine a block in the next epoch. This is how it goes. It's simple as that. No races, no like once you've proved that you have stored the storage, you know exactly at what point, at which layer you will be creating a block. Okay, so how does this work? Basically, you prove to the network using an activation transaction. Once this whole process is done, you release an activation transaction for all other miners to see. In this activation transaction, you have what we call a non-interactive proof of space-time, which is exactly what it sounds like. It's a non-interactive proof. Non-interactive means you don't need to communicate with other nodes for you to know that this proof of space-time is correct. You have the proof of space. Basically, it's a hash telling that you have stored this exact space, and you haven't like erased it and created a new one altogether. And you have a POET proof. A POET is proof of elapsed time. Proof of elapsed time basically means that somehow we prove that time has passed and that this storage is still the same. So once you release this activation transaction, as I said, you will be eligible to create a block in the next epoch. And you will also be able to participate in HARE consensus protocol. So the blocks you will produce is how much is in correlation with how much space you have stored, and how much of it is as part of the total space committed in this epoch. Okay, so these numbers can change from epoch to epoch. There could be one epoch where you will be creating one block, or other epochs where you'll be creating more than one block, according to how much total space committed in this epoch. So blocks positions are determined by what we call a verifiable random function. It's basically a random function that is shared among all miners and can be verified to be correct by all other miners.
Anton,
Okay. Yeah.
Unfortunately, we have to cut here.
Okay.
Yeah, we have to cut at the hour. But you know, this is super interesting. I guess one thing I would just ask is if it's possible to share the deck. I don't know if you guys want to do that.
Sure, no problem.
I can share that with the community as well. And then I'll follow up with you separately as well. This was super interesting though. I'm sure everybody's going to enjoy this. You know, when they get to see the video, I think it's good to see kind of like a new thinking around, you know, kind of how to do consensus in a different way that doesn't compromise security, but still potentially has some of the, you know, unique attributes that, you know, we wanted in the first place from blockchains, right?
Yeah, that's exactly what we're all about. Cool.
Exactly.
Okay, so I wish I haven't talked this much about Bitcoin now, but I guess it's all good. Thank you guys for having me. It's been a pleasure. If there are any questions like after the fact or something like that, I'd be happy to answer that in whatever medium is comfortable for you.
Sounds good. Thanks, Anton.
Cool. Thank you guys. Have a good morning.